Good morning. My name is Sudarshan Samarasinghe, and the research I am about to present today is pitch and roll control of an active Omni-Wheeled unicycle using LQR and sliding mode controller. This research was conducted at the Asian Institute of Technology under the supervision of Professor Manukit. We know there are different types of self-balancing systems like the Segway, which have become very popular, and there are many unicycles which have been researched, and many types of self-balancing unicycles have been proposed. A unicycle is unique as it is unstable in both the pitch and the roll directions, making it very complicated to control. To control it in the pitch direction, normally the cart and wheel inverse pendulum concept is used. In this concept, the system moves in the direction it is falling, and by accelerating in the direction it is falling, it retains its stability. For the roll control of such unicycles, normally gyro wheels, flywheels, and moving mass pendulums have been used. In this research, we try to present a novel unicycle which uses an active controllable omni-wheel which can move in both the pitch and the roll direction. And we try to apply the moving cart inverse pendulum concept in both the pitch and the roll directions. In this research, we present the Omni-Wheel, which is actively controllable. Here we have a fully decoupled Omni-Wheel, where there are two shafts, one for the pitch and one for the roll. The roll and pitch shafts are completely independent. The roll shaft is connected to a bevel gear system which controls the rollers, and the pitch shaft is directly connected by a hub to the wheel which directly controls the wheel. The bevel gear differential system is used for the roll control of the Omni-Wheel. As can be seen here, the roll shaft is directly connected to the bevel gear system. There is one central bevel gear. There are 4 surrounding bevel gears, and these are transferred by mitre gears and sprocket and chain system to the rollers. There are double universal joints have been used to connect all the rollers so they move as one concentric circle. All the rollers are connected. There are 4 active controlled universal joints and 4 passive controlled universal joints, and all these rollers and gears rotate together and are controlled by the roll axis shaft and motor, as can be seen. There are 2 separate motors, one for the roll axis and one for the pitch axis. The pitch axis shaft is directly connected to the wheel and directly controls the wheel, the entire Omni-Wheel, while the roll axis shaft through the bevel gear system controls the rollers. So the 2 motors also are geared and are connected to each shaft independently and are fully decoupled. Here you can see the full system implementation. Then we come to the pitch dynamics. Here in the pitch dynamics, you can see the cart and wheel inverse pendulum concept has been applied. So the wheel is the entire Omni-Wheel. The rotation of the wheel is beta and the leaning angle of the body is alpha. And we try to control alpha and keep it at 0 by moving beta. So the acceleration on beta is from the DC motor. So we can obtain the equations using the position vectors. The inertias are calculated about the center of gravity of the wheel. And here you can see using the Euler-Lagrange methodology, by getting the kinetic energy and the potential energy, we can get the Lagrangian, and then we try to get the dynamic equations. So the force, the external force, is the torque acting on the wheel. This is from the DC motor. From the DC motor equation we can get the voltage relationship, and we try to apply DC voltage control to control beta, and then by the reactive torque we try to control alpha and keep it at 0. So this is an under actuated system, and that is why it is unstable. After linearizing for small angles of alpha, we can get the dynamic equation. You can see that the poles are unstable. We get the full state space control alpha alpha dot, beta, beta dot. The roll dynamics is similar. Here the only difference is the entire body is the rest of the whole wheel, the motors and the body. For the wheel we are using only one single roller. So one single roller acts as the wheel and the rest acts as the body. So here we try to apply the similar dynamic system for this as in the pitch axis. So similarly, using the Euler-Lagrange, we can get the dynamic equation. It is similar to the pitch axis dynamics, but the parameters only are different, and we can see that it is very unstable. The controllers we have used LQR and sliding mode. We are using full state control, so we have encoder to get the wheel angle and wheel angle acceleration, and the IMU to get the body angle and body angle acceleration. Using the optimal control, we can get the gains at using LQR. Then we can use sliding mode controller, which is a robust controller for unmodeled disturbances. We can get the sliding surface, and as previously shown in literature, we decouple the entire dynamic equation using the decoupling transformation, as this is a under actuated coupled system for a single axis. You can see from the equations how it is coupled. The U is coupled to two state space variables. We use the decoupling transformation as shown in literature to decouple this system. We get the sliding mode surface, and we can then use the Hurwitz stability to get the gains and how we can tune and control the control law. We have obtained results using simulation and experiments for both axes. So in the pitch axis LQR simulation, you can see there is an initial disturbance has been given, initial state has been given, and the system converges to 0, and the gains have been proposed by the LQR control law from the MATLAB, and we can see that the system is controlled within about 4 seconds. The system reaches stability in all 4 states. In sliding mode controller, we can see similarly it is also easily stabilized with the gains that have been used. Here you can see that the system is more aggressive and the gains have converged the system faster than LQR. In the experiments, we can see the pitch axis experiments. There are two types of experiments that can be conducted. In the pitch axis, the wheel is very large as it is the entire Omni-Wheel, and the body is somewhat lighter as it is only the motors and the aluminium frame. In this system, we can balance the entire system on a single roller. And this is what can be seen in the first experiment. The whole system is balanced on a single roller as a normal wheel. In the second experiment, we can give a disturbance, then the system will begin to move more. As it moves, it will move from one roller to the next. And this is where it acts as an Omni-Wheel, because when it is moving from one roller to the next, there is a gap between each roller, which you do not find in a normal wheel. And when it is moving from this gap, there is a jerk that is created, a self-disturbance. And this jerk tends to create some shocks in the pitch axis. And we can see that the pitch axis body angle on the left, the pitch angle with LQR is the body angle alpha. We can see that the system becomes disturbed and then it regains its stability because of the controller action. So even though it is disturbed because of this jerk that is created by the rollers, by the gap between the rollers, we can still see it regains its stability. So this happens between the 3rd and 4th second and the 8th and 9th second. Then we can see in the video, you can see this more clearly. So we have decoupled this. Therefore, we are balancing only one axis at a time. So we can see the pitch direction, it is very unstable without a controller. After applying the controller, we can see that it is stable. And even when we give a disturbance, it is still able to control the system. Now it moves between rollers. You can see it becomes quite unstable, but the controller is able to regain the stability. So this is on a single roller. Again, within a single roller, it can still maintain the stability. Then in the sliding mode controller also we see similarly the sliding mode controller is quite aggressive, but it is able to keep the stability even while moving between the rollers. So you can see in the sliding mode controller pitch video, it is still able to keep the stability. You can see that it is quite aggressive, but it is still able to keep the stability. Then we see the roll axis simulation with LQR. Here in the roll axis also you can see that the gains are able to control the system, but when we look at the roll wheel angle and the roll wheel angle rate, we can see it is very high. We can see that a high acceleration is required to stabilize this system. This is because the wheel is just a single roller and it is very small, while the entire body is the whole Omni-Wheel and the entire aluminium frame, the motors, everything counts as the body. And this is very heavy, and therefore a very high acceleration and torque is required to stabilize this system. So in the sliding mode also we can see similarly, not unlike the pitch, for the roll we need a very high acceleration to stabilize the system. And practically when we apply this controller, we can see that in the experimental results the system cannot be stabilized. It is very difficult to stabilize this system even with LQR and sliding mode controller. So this is the body angle that you can see, and we can see that in this body angle the state does not converge, that the roll angle, which is the body gamma, it is not being brought to stability, and this is because of the roller has to move with a very high acceleration, and it cannot gain that acceleration with the gearing system and with the chains and the sprockets and the backlash. It is unable to bring this system to stabilization. So in the video, this video has been done with PID, but you can see the concept, and we see similar results with the other controllers also. Here we keep the pitch angle stable and we are balancing only the roll, and we can see that it is unable to bring it to stability. It becomes rapidly unstable. So in conclusion, we can say we have presented the design and control of a novel omnidirectional unicycle. We have presented a design for this active omni-wheel using a decoupled pitch and roll design. We have designed the decoupled controllers using LQR and sliding mode controller. We have derived the dynamics and control, and we have applied this in simulation and also demonstrated it using experiments. In the simulation and experiments, we can see that the pitch axis can be balanced, and even with the unmodeled disturbances created by the Omni-Wheel design in the pitch direction, because of the gap, the roll controllers are still able to robustly balance the system. We see that this weakness of this design in the pitch direction is the gap between the rollers, and this is an inherent weakness of an Omni-Wheel, and which needs to be further improved as it can create unmodeled disturbances in the pitch direction. In the roll direction, we can see with the simulation and experiments, it is difficult to stabilize this system because the roller is very small, has a high gearing system, and the system is highly unstable because of the heavy body. So this needs a streamlined design of a faster transmission system to balance this sort of system in the roll direction. Thank you.